Did you know that a cup of coffee left on a table will eventually become the same temperature as its surroundings? This isn't just a random occurrence. Instead, it is a manifestation of one of the fundamental laws of nature, commonly referred to as the second law of thermodynamics. Now you may find yourself wondering, what is so special about this particular law? Why should it matter in the grand scheme of things? The second law of thermodynamics is not just an abstract concept in physics, it is an essential principle that governs the natural world, a universal rule book that nature adheres to. Whether it's a cup of coffee cooling down on your table, a log crackling and burning in a fireplace on a cold winter's night, or even the sun itself, radiating waves of energy into the vast expanse of space, the second law of thermodynamics is at play. To distill it into its essence, the second law of thermodynamics states that the total entropy or randomness of an isolated system can never decrease over time. But what exactly does this mean? How can we comprehend such an abstract idea? Imagine a box of marbles, each one a different vibrant color, all neatly arranged by hue. If you were to pick up this box and shake it, the marbles would jumble and mix, increasing the randomness or entropy of the system. No matter how long or how vigorously you shake the box, it's extremely improbable that the marbles would ever return to their original order. This is a rudimentary but effective way to understand the second law of thermodynamics. But the implications of this law go beyond mere marbles in a box or a cooling cup of coffee. It is a fundamental principle that offers us insights into how energy operates and why specific processes take place as they do. It presides over everything from the power plants that generate our electricity to the cells in our bodies that keep us alive. The second law of thermodynamics is always active, dictating that energy must flow from areas of high energy to areas of low energy, thereby increasing the total entropy of the system. So the next time you notice your coffee has cooled down, remember that it's not just a random event. It's the second law of thermodynamics in action, directing the flow of energy and increasing the entropy or randomness of the universe. It's a profound concept, isn't it? A law so simple yet so impactful that it governs everything from a single cup of coffee to the vast cosmos itself. So the next time your coffee cools down, remember it's the second law of thermodynamics at work. Now that we've covered the second law, let's delve into a concept that it heavily relies on: entropy. This seemingly elusive concept is actually a state function, meaning its value is determined by the current state of the system, independent of the path taken to reach that state. So what exactly is entropy? Well, in the simplest terms, it's a measure of randomness or disorder within a system. Imagine you have a box of colored balls, red, blue, and green. If these balls are neatly arranged by color, we would say the system has low entropy, as there's a high degree of order. But if you were to shake this box, and the balls got all mixed up, the system would now be more random, and thus we'd say the entropy has increased. Now, why does entropy tend to increase? This is a direct consequence of the second law of thermodynamics, which states that in an isolated system, the total entropy can only increase over time. This is because natural processes tend to move towards a state of equilibrium, which is the state of maximum randomness. Just like our box of colored balls, given enough time and no interference, they will eventually end up in a mixed-up, random state. But why is this important? Well, understanding entropy helps us predict the direction of a spontaneous process. If a process results in an increase in total entropy, it will likely occur spontaneously. On the other hand, if it results in a decrease, it's going to need some external help to occur. In essence, entropy is a bit like the universe's inclination towards chaos. It's a fundamental principle that governs the natural world, from the dispersal of perfume in a room to the melting of ice in your drink. In the world of thermodynamics, chaos isn't just a pit, but a ladder, and that ladder is entropy. So next time you see something becoming more disorderly, remember, it's just the universe adhering to the laws of thermodynamics, climbing the ladder of entropy. So we have a law and a measure of randomness. But how do we know if a process is spontaneous or not? Enter Gibbs energy. Let's imagine Gibbs energy as the thermodynamic potential. It's a bit like a superhero in the world of chemistry, swooping in to give us the answers we need. So, what is this superhero's superpower, you ask? It's predicting whether a chemical process will occur spontaneously or not. Gibbs energy, denoted by the letter G, is named after the American scientist Josiah Willard Gibbs. It can be defined as the maximum reversible work that a system can perform at constant temperature and pressure, excluding work done by pressure-volume work. Now, let's talk about spontaneous and non-spontaneous processes. A spontaneous process is one that occurs naturally, without any external influence. Think of a ball rolling downhill. It doesn't need a push, it just goes. On the other hand, a non-spontaneous process is one that needs an external influence to happen, like pushing that ball uphill. Gibbs energy helps us figure out which of these two scenarios we're dealing with. If the change in Gibbs energy, or dg, is negative, the process is spontaneous. If dg is positive, the process is non-spontaneous. But what about when dg equals 0? That's when we're at equilibrium. The forward and backward reactions are happening at the same rate, so there's no net change. So, in essence, Gibbs energy is a bit of a fortune teller. It helps us understand the thermodynamic feasibility of reactions, telling us if a reaction can occur under the given conditions or not. It's crucial to remember that Gibbs energy does not predict the speed of the reaction. A reaction with a negative dg could still be very slow. It's more about the will it, won't it, rather than the how fast. Gibbs energy, a little like a crystal ball, helps us predict the will it, won't it of chemical reactions. Finally, we arrive at the third law of thermodynamics, a law that takes us to the absolute zero of temperatures. Now, you might be wondering, what does this even mean? Well, let's break it down. Imagine a perfect crystal. Now, a perfect crystal is a bit of an idealization, but it's a useful one. It's a structure where every atom or molecule is perfectly arranged, with no disorder or randomness. Now, imagine this perfect crystal at absolute zero temperature. Absolute zero is the lowest possible temperature, a chilly minus 273.15 degrees Celsius, where all thermal motion stops. According to the third law of thermodynamics, the entropy of this perfect crystal at absolute zero is 0. But what is entropy again? It's a measure of the randomness or disorder in a system. So at absolute zero in our perfect crystal, there's no randomness, no disorder, and thus zero entropy. Why is this important? The third law gives us a starting point, a baseline if you like, for measuring entropy. Without it, we'd be a bit lost, like trying to measure distance without a 0 point on a ruler. It's important to remember that entropy is a state function, dependent only on the current state of the system, not how it got there. The third law, in essence, gives us an endpoint, a 0 to measure all other entropies against. This allows us to make sense of the complex world of thermodynamics. And there you have it, a quick journey through some of the fundamental concepts of thermodynamics. We've explored the intriguing second law, delved into the measure of randomness with entropy, discovered Gibbs energy as the thermodynamic potential, and touched upon the absolute zero with the third law. We'd love to hear your thoughts or questions about these concepts. Don't forget to like, share, and subscribe to our channel, Facts Academy 0122, for more captivating science content. Thank you for watching and keep exploring the world of science.